There are an awful lot of elements in the periodic table, with different combinations of electrons and orbitals. How can we make sense of all that information in a concise way to understand how each of these elements will react? The answer lies in something called effective nuclear charge. And that's the focus for today. All right, now that we understand how to do an electron configuration, which is really just a listing of where all of our electrons are and all of the different orbitals, how can we use that to make some sense of the chemical behavior of an atom? Well, the first thing I would remind you of is that most chemical behavior really has to do with charges, right? These are charged particles flying through the universe. So positives attract negatives and vice versa, and like charges repel. And it's really charge-charge interactions that govern an awful lot of the chemistry that we're going to discuss this semester. So one of the things that I think would be most instructive for us to do is to think about what those charged interactions are in a particular atom. So let's not forget that these are all of the orbitals we have available to us. And of course, I'm not forgetting the fact that there are more higher energy orbitals, but I'll use these ones that we can see on the screen here just to conceptualize a point that I want to make today. We first of all realize that our low energy orbitals are smaller. They tend to be smaller in size. And as we increment that principal quantum number and go up to principal quantum number 2, we get different shapes, but they're all bigger than principal quantum number 1. Likewise, at principal quantum number 3, again, we get similar shapes, but some new ones as well. But the take-home message here is that they're all bigger. In other words, as we go to higher principal quantum numbers, the electrons that are in those orbitals are spread farther out in space from the nucleus. So let's remember that the nucleus is always positioned at the center of all of these axis systems. And so the electrons in these orbitals are able to spread farther out in space, and generally they do. Now, this shouldn't be surprising because electrons would want to be close to a nucleus, and so it would be a very low energy or very stable scenario to have electrons very close to that nucleus, negatively charged electrons next to positively charged protons. This is a good situation, coulombically, and would therefore cause a low energy scenario. And likewise, as we go up, if we spread those electrons farther out, that is okay, but not quite as energetically favorable as, say, the 1s. Now, why wouldn't electrons in a 2s state want to get closer? Well, of course they would, but they'd be prevented from getting closer because of these two electrons closer in the 1s. It's those two 1s electrons that are preventing any of the 2s electrons from getting any closer to the nucleus, and so on and so forth. The same can be said for the 3s electrons. And even the 3Ds. All of those outermost orbitals, the electrons in them have a harder time getting close to the nucleus because you have these smaller ones that are already there, already closer. So what I'd like to do is put some math to this, even if it's only some approximate math. So let's imagine the following scenario. Suppose we have a nucleus with some protons in it, and we can envision the various spatial zones in the vicinity of that nucleus to help give us an idea about where electrons would be spending most of their time and which electrons would be those privileged few that would be able to get extra close to the nucleus. So imagine, I'm just going to draw a schematic diagram here where I've got this small zone around a nucleus, and inside that zone would be my n=1 zone, that closest zone to the nucleus. But let's imagine we've got other zones, like what about the n=2 zone? We know that the electrons in orbitals having principal quantum number 2 are generally going to spend their time further away from the nucleus because those two electrons in the n=1 zone will block them out or shield them out. And that's a concept that's important. Now, We could continue on and say we've got even another zone even farther out from the nucleus. And again, there'll be electrons in this zone that have a really hard time getting close to the nucleus, which is what they'd want to do, because not only are there other electrons within this smaller zone, the n equals 1 zone, but there's electrons spending their time in this zone too, in the n equals 2 zone. Now, keep in mind that this is just a schematic diagram where I'm drawing these zones as circles of different radii, but you know what the shapes of those orbitals actually look like. But for the purposes of the argument I'm trying to make here, this diagram will suffice just fine. So what we can do is we can ask ourselves the question, if I have electrons spending time out here in this farther zone, what force, or what is the force compelling them to stick to this atom? Why wouldn't they just fly off and go somewhere else? Well, obviously we know that the force compelling them to stay is this nucleus, this proton, or series of protons right in the heart. This is a lot of positive charge, and presumably that's enough positive charge to hold all of the electrons and keep them in where they are, and draw them all as close as possible. And just because these outermost electrons can't get directly inside on top of the nucleus, doesn't mean they're not still held in their outermost place by the protons that are here. And so what we really need to think about in terms of thinking about charges back and forth is, what is the effective nuclear charge that holds these outermost electrons? We always know what the actual nuclear charge is. That's just the number of protons in the nucleus. And we write that generally as the letter Z. And so we know how many protons are there. The question is, how many protons do these outermost electrons feel? Because they probably don't feel the full attraction to all the protons, because there are other electrons in these zones that repel. You see, there's a balance of forces here. These electrons are attracted to those protons, but repelled by the interstitial electrons that are closer to the nucleus than they are. And so that's an important concept to think about. These outermost electrons are the ones that are going to be doing most of the chemistry of this system. As two atoms come into contact, it's their outermost electrons that will do the bonding or do whatever chemistry is meant to happen, because they're the first electrons that come into contact with their neighbor. So it's really important for us to understand how these outermost electrons will behave. And the fundamental concept for us to understand how these outermost electrons will behave is to understand with what force are they actually attracted to this nucleus. How capable is this nucleus of holding all of the electrons in the system? Now, to do this, we are going to determine something called an effective nuclear charge. Not the actual nuclear charge, but an effective nuclear charge. A nuclear charge that is adjusted to account for the fact that there are other electrons as well as protons in this system. And how this effective nuclear charge is calculated is we start by taking the actual nuclear charge of a particular system, and we subtract from that some amount of what we call shielding, or S. In other words, for the electron, say, out here in this zone, how much is that electron shielded from the nucleus based on the other electrons that are in its way? So that's really what we're concerned about here. We're concerned about counting how many electrons are in the way of the electron that I'm thinking about at the moment. And most often, we think about the outermost electrons in these systems. So really all we have to do, because Z is a pretty obvious number, for whatever element we're speaking about, we know Z. What we really need to think about here is S. How can we predict how much other electrons shield a particular electron? Okay, so the way that this is typically done is by using a set of approximate rules, which are known as Slater's rules. So these are guidelines to help us understand what the impact of electrons are around a nucleus on how well that nucleus is able to attract outermost electrons. So these rules, called Slater's rules, will help us understand that value of S. It helps us predict that shielding amount. And so to really illustrate this, I think it's best to do so with an example. Let's imagine, if you will, the magnesium atom. So the magnesium atom might make a suitable example here. So magnesium, you should already know at this point how to do an electron configuration for magnesium, but magnesium is element number 12 in the periodic table. So if we're thinking about neutral magnesium, we simply occupy the lowest energy orbitals all the way up until we have 12 electrons accounted for. So we can see that we'd have 1s2, 2s would have 2, 2p would have 6, so these are all full, which gives me a total of 10, and then I can finish this off by saying 3s2, okay? So this would be the electron configuration of magnesium, and just to put a little bit more context in my diagram, I can recall now, of course, that there are 12 protons in magnesium. But here's the thing. What I want to know is I want to place my electrons, these ones, at least conceptually over in this diagram. Now, placing these electrons in this diagram is not something that you'll practically need to do to answer problems. I'm just doing it here for us today to give us a sense of what this actually means. So let's think about this. I know that I've got 2 electrons in my 1s shell, or in that first principal quantum number. So really that tells me that I've got 2 electrons spending time in this inner zone, right? And they're really good at blocking out or shielding other electrons that are further away from the nucleus than it, because they're greedy. They are closest to the nucleus. They have this privileged position, very low in energy, and they will get in the way, if you will, of these other electrons. And really all of the electrons will do that to some extent. When we go out to this spatial zone out here, a little bit further away from the nucleus, that would be all of these principal quantum number 2 electrons, of which we can see there are 8. So there are 8 electrons spending time in this intermediate zone here. Again, all of them trying to get closer to the nucleus, but generally being blocked out by the 2 that are inside. And this diagram isn't necessarily to scale. Again, it's just a schematic to try to give us an idea. And then finally, out in the 3, the n equals 3 level, we can see that there are 2 electrons out here in this zone, and that's signified by the 3s2 that we've got over here in our electron configuration. So here's the thing. I'd like to know with what force, or what is the effective nuclear charge. I know what the actual nuclear charge is. There's 12 protons there. There's a charge of plus 12. And I want to know, does this charge of plus 12 effectively hold on to all of these electrons? Are all of these electrons, these 12 electrons, well bound to this proton? And the reason it's not a simple calculation is because these electrons are all moving around and they're all in different spatial positions. And this is what Slater's rules is useful for. It's useful for us to conceptualize really how well these 2 electrons here, can be bound to this proton. And to be clear, we can do the sort of calculation I'm about to show you for any electron in any spatial zone. It's just most often that we think about the outermost electrons because, as I said before, they're the ones doing the majority of the chemistry. When atoms come into contact with one another, it is their outermost electrons that are the first to interact. All right, so let's think about this. What Slater has done is Slater has essentially devised 3 different types of shielding. Okay, so there's 3 different types of shielding that can be at play. And this example, this magnesium example, will allow me to show those to you. So let's first imagine that we are one of these outermost electrons. Okay, from a Slater's rules perspective, we are imagining that we are one of those electrons, and the exercise becomes, let's count all of the other electrons. That's really key. So if I'm one of these electrons, how many other electrons are there? So if we first consider this outermost zone, we know that there's 2 electrons there. So if I'm one of those electrons, there is 1 other electron with me. Now, what Slater's rules tells us is that the shielding value for electrons that are in the same spatial zone as you are is 0.35. Now, what does that mean? What does this 0.35 mean? One of the conceptual ways of thinking about what that means is you could say that the second electron in this zone shields me from the nucleus about 35% of the time. That's one of the ways to interpret this number. So there are two electrons out here in the spatial zone. We're orbiting or spending time, whizzing around the nucleus in some way. And there is a second electron with me. And because this zone is so big, I can spend a lot of time away from that other electron. And so I might imagine that 75% of the time, or the vast majority of the time, that other electron isn't in my way at all. And so if I'm really more concerned about, well, how much does it shield me from the nucleus? How much time does it spend in front of me, right? How much time does it cross in front of me and shield me from the nucleus? According to Slater's rules, we give electrons a value of 0.35. So we will say that the other electron out here shields me from the nucleus about 35% of the time. All right, now, there are other zones, obviously. What about these 8 electrons, right? If I'm one of these two out here, then there are 8 others in this intermediate zone. And what Slater's rules tells us is that for electrons that are one zone closer to the nucleus than you are, so they're closer than you are, so they are more effectively shielding you, Slater's rules gives those electrons a value of 0.85. In other words, we say that those electrons are shielding the outermost electron 85% of the time. So each and every one of them is in front of the electron I'm interested in 85% of the time. So much more effective at shielding out the electrons on the outermost region here. And that makes sense because they're in a smaller region. They can more easily get around and block the nucleus from the electrons on the outer side. And then finally, we've got yet another spatial zone here, this innermost zone. What Slater's rules tells us is, and Slater's rules really only defines 3 different zones. Slater's rules defines the zone you're in, one zone closer, and then really anything closer to that, or anything closer is going to get the same value. And the shielding value for electrons in those zones is a full 100%. And so it's assumed that electrons in this tiny little 1s zone spend so much of their time, it's so easy for them to be in front of the nucleus and block out every other electron beyond it, that any electron out in this 3 zone here is blocked 100% of the time by electrons that are in this inner zone. Now, to stitch all of this together, we want to add up the effect. What is the shielding effect for all of these electrons? What we'll do is we'll just put all that together here with a bit of math. So our shielding will be taking into account that we've got one additional electron out in that 3rd zone that is shielding me with an amount of 0.35. Right? Now remember, there are 2 electrons in that outermost zone, but only one other one, because I'm imagining that I'm that first electron. An effective nuclear charge is always from the perspective of a particular electron. So we've got one other electron in the same spatial zone as me, and then we've got 8 electrons in the zone inner to that, directly inner. And each of those 8 electrons will shield me 85% of the time. And then finally, we have 2 electrons that are in the 1s, or 2 shells in from where I'm currently standing. And each of those electrons, in fact, any electron further in than this zone, will shield with 100%. So if I add all of that up, my 0.35 plus my 8 times 0.85 plus my final 2 there, that would be left. What I'm left with is 9.15. So what is this? This is the effective amount of shielding. This is the amount of shielding or blocking that all of these inner electrons, including that additional one out with me in that 3s level, all of those electrons are blocking me to an extent of about 9.15. That's the amount of the nucleus that is being blocked by those other electrons, or shielded by those other electrons. So now I can use my equation for the effective nuclear charge. Let me just slide it up out of the way a little bit to calculate what my effective nuclear charge actually is. Let's remember that in this case we're dealing with magnesium, which has a nuclear charge of 12, and we are shielded by about 9.15 of that charge. So 12 minus 9.15 is equal to 2.85. So what does this mean? What does this 2.85 actually indicate? What the 2.85 means is that my outermost electron here is attracted, or feels a nuclear charge of 2.85, not at all 12. It doesn't feel attracted to the system as though there were 12 protons in the core. What it feels is an attraction to something that would be about 2.85 protons here in the nucleus. Now that number in and of itself isn't necessarily that useful until we start comparing it with the number we might get for other atoms in the periodic table. So let's do that now. Let's move one position to the right on the periodic table and talk about aluminum. You'll notice I've taken the liberty of writing out the electron configuration for aluminum, which is really the same as magnesium except for this one extra electron at the 3p level. And I've indicated that extra electron up here, reminding me that I've got now 3 electrons out here in this same spatial zone, remembering that the principal quantum number here defines the zone. So 3 in total in that n equals 3 level. I've also jotted down the effective nuclear charge that we previously calculated for magnesium, just for quick reference. So now let's do our Slater's rules calculation again, assuming that we are one of these outermost 3 electrons. We start by asking ourselves how many other electrons are with us in this spatial zone. And again, we realize that if we are one of those electrons, there are 2 others with us. So to indicate that on our calculation down here, we will recall that there are 2 electrons with us in our same spatial zone. Note that this is actually the key difference in this calculation. The other key difference that I've not yet indicated here is our effective nuclear charge, our actual nuclear charge. As we move from magnesium over to aluminum, we add another proton. And so our actual nuclear charge becomes 13. And so these are the 2 key differences between magnesium and aluminum, one step to the right on the periodic table. We add an extra proton, and we add an extra electron that is shielding me out in the outermost n level. Now, the other values will generally be exactly the same. So here, in terms of counting the number of electrons that shield me at 85%, again, I have 8 at that level. And counting the number of electrons that shield me completely one step in is again 2, thanks to the 2 electrons that are in the 1s orbital. Now the result here will be that our value for S will be slightly different than our previous value for S. We will have an additional 0.35 because now this is being multiplied by 2. And our total value for shielding is now 9.50 instead of the previous 9.15. Now using this value for my shielding constant, 9.5, I can now calculate my effective nuclear charge. Recalling that for aluminum, my actual nuclear charge is 13. If I take 9.5 away from that, we can see that my new effective nuclear charge is 3.50. Now let's take a look at this number. 3.50 is my new effective nuclear charge. I can compare that to the effective nuclear charge of magnesium. Now for a system that is relatively very similar, my outermost electrons in magnesium are only bound to the nucleus as though it had a charge of 2.85, whereas my outermost electrons in aluminum are bound to that nucleus as though it had a significantly larger charge of 3.50. We can use simple arguments like this in Slater's rules to rationalize the fact that these outermost electrons in aluminum must be more tightly bound to that atom because of all this shielding argument. The fact that there are the same number of electrons inner here shielding me, but there is an additional proton, means that my outermost electrons in aluminum are more strongly bound than my outermost electrons in magnesium. And we can use these arguments for explaining so many different chemical properties. It is clearly more difficult to remove an electron from aluminum than it is from magnesium. And so if we think about that same effect, the fact that the effective nuclear charge for that outermost electron on aluminum is greater than that of magnesium, and then we take a look at a periodic table of elements, reminding ourselves that magnesium is here and aluminum is here, we see that guaranteed as we go to the right on the periodic table, the effective nuclear charge will get stronger and stronger and stronger. And that tells us that the outermost electrons for these elements are going to be more tightly bound as we move across to the right. Now, we haven't done anything with that information yet, but you can already tell that the electrons for something like argon are going to be very tightly bound and not likely to leave the atom. Contrast that with electrons on something like sodium, which are going to not be very tightly bound and are going to be potentially lost much more easily. So you can clearly tell that argon is more likely to be an inert element, something that isn't likely to react very much. And I don't know what your familiarity with the periodic table is, but these are what are called the noble gases. And they are inert. They don't react very much. Contrast that with group 1 in the periodic table, which has very reactive elements. And so we can already start to envision why that is, just using simple arguments about building up where electrons are in a particular element and how they shield out the outermost electrons from the nucleus. And just doing some simple arithmetic can allow us to predict which electrons will be more tightly bound, or more specifically, which elements will have its outermost electrons more tightly bound. Now you can do these same sorts of calculations, these Slater's rules calculations, with any electron. It doesn't have to be one of the outermost electrons. So for example, you can talk about how strongly bound are these 2s2p electrons. You could ask, how much do these 1s2 electrons shield out those ones? But Slater's rules essentially works in the same way for that system too. I put a handful of problems in this week's problem set for you to work out the Slater's rules of all different sorts of elements. So give those a try, and using arguments around Slater's rules like we've done here, we are going to explain ionization energy, the size of elements, electronegativity, electron affinity, all of these properties coming up in the next lecture.